Hi everyone, I'm Hirushie. This video is based on the work I carried out under the 40 Species Smart Energy Champ, a collaborative MITAX research project between the University of British Columbia and 40 Species. This work was carried out during my time as a postdoctoral research fellow at the Lifecycle Management Laboratory of the UBC-O School of Engineering. One theme we tackled under this project was clean technologies and climate change mitigation. In that, my work was mainly focused on net zero communities and specifically the development of renewable-based hybrid energy systems. The principal investigator of this project was my supervisor, Dr. Cousin Havergate. Now, while there's a lot of attention and hype with regards to decentralized hybrid energy systems, communities face quite a bit of challenges when implementing them. One of the most significant barriers in this effort is the lack of structured decision support and guidance on how to develop the best energy systems and how to deploy the community energy projects for the best outcomes. So, our attempt was to help in overcoming this gap through our work. The objective of this research was to develop decision support models for selecting the best energy supply sources and technologies and identify the optimal energy mix for hybrid decentralized energy systems. This research was carried out in 5 interconnected phases, and the first phase had the literature review and the database development, and the inputs from that was used in the next 4 phases. Ultimately, the decision support tools and best management practices were developed from the research outcomes, and these were further refined. So if we take a look at the work step by step, in the literature review, the commercially viable renewable energy sources and technologies were reviewed and identified, and the assessment criteria for selecting renewable energy technologies and the performance criteria for developing the best community energy systems were defined based on literature and previous work done in this area. The constraints and requirements for developing community energy systems were identified during this phase, and also we investigated suitable multi-criteria decision-making methods for technology ranking and system optimization. Now, this is needed because community energy systems, the development of community energy systems, it has conflicting goals to minimize the energy costs, to minimize the environmental damage, to maximize the social benefit. All of these things, all of these performance goals, they conflict with each other. And this is why we need multi-criteria decision making every step of the way. In the data collection, we identified the performance characteristics of all the individual renewable energy technologies and carried out a life cycle assessment and life cycle costing for the technologies based on that. We also collected data under various social categories such as job creation and human health impacts of various energy technologies. In the next phase, the specific indicators, the key performance indicators were developed to represent the assessment criteria for renewable energy technologies and energy systems, and the benchmark performance ranges were identified. And the life cycle cost model and the life cycle impact models, they were further refined and developed to accommodate combined energy systems. We also used a fuzzy logic approach to integrate uncertainties in the decision making. So the next step was to rank renewable energy technologies based on their aggregate performance under the different indicators and to prioritize the best technologies for a given energy system. Following that, after screening and selecting the technologies, we carried out the energy system optimization. Here we explored quite a number of possible optimization methods in order to identify what is the best method in this sort of application. And we defined the objective functions for economic, environmental, technical, and social criteria, and simulated all the possible energy system combinations, and assign weights to the performance objectives based on decision maker priorities. And again, a fuzzy logic based approach was used in the initial optimization to integrate the uncertainties. Later, we used goal programming and robust optimization in order to carry out the same optimization while accounting for the stochasticity and uncertainty with a lower time consumption in the decision-making process. Based on this, we developed multi-criteria optimization models for planning renewable energy systems at building level and at community level. Now, energy system planning is not of a static nature. It's a dynamic process. Things evolve, energy prices change, technologies evolve, and resource availability can change, even the demand of communities and buildings. These things can change. So we try to identify what is the best way to deploy an energy project of this nature. How do we select the best projects? For this, we took a system dynamics approach to assign suitability ratings for different energy project implementation strategies. And we extended the decision support tool further with this. Ultimately, all of these things were used in developing the decision support framework and the best practices for communities to support the stakeholders, the community energy planners, decision makers, local government, the residents, everyone in planning the best energy systems to suit their unique individual needs. Now, moving on to the findings. We have several findings in this study, but out of them, I'm going to summarize the most interesting ones. So, the bad news, what it looks like at the current status is that complete conversion to renewables, 100% net zero status is not possible at the moment due to limitations in resource availability and the difficulty in meeting grid parity. So basically what this means is we don't have sufficient renewable energy resource availability to meet the net zero status. And also the costs are somewhat prohibitive still. However, this can change with time. The good news is even with partial renewable energy integration, we can achieve significant emissions reduction. Say with even 40 to 50% renewable energy integration, we can achieve at least up to 60% emissions reduction when this is implemented at both building and community level. Now the BC grid is relatively green. It is mostly made up of hydropower. These things can change when the grid mix changes. Say we take Alberta, where the significant contributor to the grid energy mix is fossil fuels, then the emission reduction will be even higher. And solar PV, geothermal, waste to energy and biomass show the greatest potential for use in southern interior BC. While many optimization methods can be used in determining the optimal energy system sizing and mix, uncertainty integration is critical. Without that, it is difficult to find out the best, the optimal point, because it can vary in a range, in a significant range, depending on the uncertainty level of the input parameters. And stage-by-stage construction that also accounts for community growth in capacity sizing shows the best outcomes in long-range planning of community energy systems. Now, the outcomes. Now, in summarizing the outcomes, we identified models for selecting the best resources and technologies to define the optimal energy mix and the energy system type, and also on planning the facility development in the long run. Our deliverables were mostly in the form of publications, tools, and best practice guidelines. So as you can see here, we have made several publications. The goal, the main goal of our research program is to disseminate knowledge based on our work so that life is made easier for people. So with that thinking, we published 3 papers on optimal energy system planning for net zero energy buildings and communities. One of these was on specifically on optimal energy supply choices for net zero ready buildings. And the next one was about how to use goal programming in assessing the renewable energy strategies for net zero communities. And finally, we compared the various mathematical models and strategies available for energy system optimization under uncertainty. And we developed a robust optimization-based framework for community-level decentralized energy system planning. We published one conference paper on the cost of developing green residences, where part of the energy supply comes from renewable energy sources. This paper explores how housing costs can change in Canada and how environmental impacts of the building stock can change with further renewable energy integration. We published one paper on selecting renewable energy technologies for specific communities and another paper on renewable energy project assessment. How to determine the best project deployment strategies for communities with a system dynamics approach. Thank you. And I hope you enjoyed listening to that.